Hello everyone, welcome back. So in the last lecture we were looking at periodic structures, and we described the methodology to treat the periodic structures analytically. So specifically we talked about the transform matrix approach, and we said that if you are able to write the transform matrices for the various nanostructures, we can compute the electromagnetic response. And towards the end I showed you some examples, and this is one such example, the last one I believe. I didn't have sufficient time to describe it. So essentially we have a stack of layers of high index and low index, specifically 2.32 and 1.38, and there are 30 of these unit cells which are repeated. And if you look at the reflection of this structure, it looks like what is shown on the figure here. The prominent aspect here, I said, was the formation of band gap. Now, what do I mean by band gap? So, well, if I have, let's say, assume that all of these multi-layers can be described by a block like this. It's consisting of all these things along with the substrate. Now, if light is incident on this structure, what we are seeing is at 0 degrees between the wavelengths of roughly 420 or something to close to 600. In this range, the reflection is very high. So if your lambda between 420 to let's say 600 nanometers, it's getting reflected. Why is it getting reflected? The reason is that those particular waves do not have a real k vector in the material. So if I can think of this material as having an imaginary k vector at those wavelengths. Okay. So wave vector becomes imaginary. That means the wave is evanescent. Okay, and that's why you see that the light reflects. This is similar to what we talked about for metals. Even in metals, we saw that the K0, the wave vector of the particular, let's say if you have wave vectors higher than the K0, then in the medium they become evanescent, and that's why they cannot propagate, right? So this is a concept, and in today's lecture we'll try to talk about this in greater detail, how these band gaps arise and so on. So that's the agenda of this lecture. So the question was, I mentioned that it's a periodic structure. What is the typical sizes of the let's say these are multiple layers, right? What are the typical sizes? So for these particular examples, these are usually quarter wavelength, or you can choose, but typically of the order of lambda. It's not very large or very small. Okay. If it is very, very large, the thickness is very, very large, then we will consider them by geometric optics, by which I mean, my eyeglasses that I'm wearing, essentially can be treated in terms of geometric optics. So light is incident on the front interface and the back interface. The wavelength is 500 nanometers and the thickness is maybe few millimeters. So I don't need to worry. I just look at the interfaces and use the traditional optics to calculate what happens to light. And if I have the size of these periodic structures, for example, let's say I'm talking about 1D periodic structure like this, and there is a periodicity here. If the periodicity is very, very small compared to the wavelength, we said you can treat it as an effective medium. So the photonic band gaps arise when you have the wavelength which is roughly of the order of periodicity. Okay, it can be slightly lower, quarter wavelength in that particular medium, not the free space. Okay, because if you take a refractive index of let's say 4, the lambda is going to be smaller by that, right? So yeah, so that is the wavelength for which these photonic crystal effects are important. You can also understand it in terms of looking at how electrons propagate in a periodic structure. For example, any silicon, like any material, right? Solid state material, the angstrom, the lattice constant is a few angstroms. And the wavelength, when it kind of matches that scale, then you have all these band gaps and all that arising. Okay. If not, if it's a conductor, wavelengths, if you're talking of RF frequency propagation in metals, the wavelength of the electromagnetic wave is very large. So you don't have to worry about the periodic variations in the atomic scale, right? That's how you can treat it as a simple wave. So yeah, so essentially this lecture will be more of an introduction into the photonic crystals. Okay. So this domain, initially there were studies on how periodic arrangement of this light and so on. So there were wood and Rayleigh's anomalies and all that. They were there in the turn of the century. But in the recent form, the interest kicked off in the year 1987. Okay, wherein these ideas of confining light in 2 dimensions and 3 dimensions was introduced. So for example, here you see this is a periodic structure in 2 dimensions, and the 3rd dimension it is simply translated. Okay, so we call it, this is what we will call as a 2D photonic crystal. Okay, similarly you could think of a 3-dimensional photonic crystal wherein there is periodic arrangement of refractive index. No, in this case the colors represent the different refractive indices or epsilons. So you can have structures which have 3-dimensional arrangement, that is 3D photonic crystal. And yeah, as I was just mentioning, the lattice constant has to be comparable to wavelength. In this case, this become interesting. Okay, and this can be dielectrics, this can be metals. I mean, a lot of interesting things can be talked about in this context. Okay, so for today's lecture, we will focus on in this week essentially we will focus on dielectric structures. All right, and this is not something very new in the sense in the nature you find many examples of periodic structures giving bright colors. I think in the intro I mentioned about some of the structural colors. So these beautiful butterfly wing colors or insect colors and all that. If you put these things under a microscope and look at them, like this is a SEM image of a butterfly wing, you see that this regular structure is actually giving you colors. And similarly for this insect and so on. So essentially when you have these structural variations of refractive index, that can give you bright colors. Right? And so this modern form of photonic crystals was kicked off by 2 papers that were published in the year 1987 by these 2 gentlemen. So the first one was Yelai Yablanovich. He's a very famous physicist and an engineer. So he talked about what happens to spontaneous emission in a structure if it has this sort of periodicity. So essentially what he thought about was, you had these thin layers of dielectrics which were known for a very long time. What happens if you introduce such periodicity in 3 dimensions? Okay, so he sort of thought about if I look at it in a from the top, if you can arrange this dielectrics in this fashion, right? Let's say some periodic arrangement of dielectrics. So I mean you could think of this as silicon and air, or silicon and something else, right? Silicon germanium, or in his particular case, he considered I think gallium and gallium aluminum arsenide. Okay, so if you have some variations like this, and also introduce the same variations in the 3rd dimension. So this is before the launch of the pretty picture journals. So this is a very simple schematic wherein you have the 2D variation of the index here, and in the 3rd direction also you have this variation. So essentially you have he talked about a 3-dimensional photonic crystal. Okay, and he said that if you are able to do that and also make sure that the photonic band gap coincides with the electronic band gap, then it is possible to inhibit spontaneous emission, and that can have far-reaching implications. Is what he proposed in this PRL in the year 1987. Okay, so immediately a couple of months after that, I believe, or even less than a month after that, there was another paper by another physicist by name Sajeev John. He considered a completely different structure. While Yablanovich looked at periodic arrangement of dielectrics, lattice, perfect lattice of dielectric constants or other dielectric materials, Sajeev John considered what happens if you have a random or disordered dielectric lattice. So it's a very surprising thing he found, that even in such scenario wherein you have this disordered dielectrics, that means, to give an example, if you looked at the snowflakes, there would not be any perfect arrangement. There would be some sort of distribution in that, some random distribution. Okay, or if you spill some oil on water or something, if it's tiny droplets, they'll not form any regular arrangement, but form some sort of random structure. So if you have such a scenario, he found out that there's going to be a sharp gap in the density of states in such structures, and that's what he called as a band gap, or in this case strong localization band gap, he said. This also goes back to the theory of Anderson's localization and all that in the electronics. So he tried to borrow some of those ideas and introduce them in the photonics. The surprising thing is, how can a band gap exist? Essentially, what is a band gap? When there are no density of states. So what you're seeing here is that the density of states is exhibiting a sharp dip at certain frequencies. And, but how can you think of a band gap in disordered medium? That's a very perplexing thing. But in fact, it turns out that even if you take glass, we sort of talk of a band gap. Glass is an amorphous material. You might think that, oh, it's an amorphous material. There is no periodic arrangement. How can it have a band gap? But it has what is known as a pseudo band gap. You can think of it. So essentially, there are two things: short range order and long range order. So basically, the disorder length scale will decide the existence or not of the band gap. All right. So anyway, this is all a little bit beyond what you need right now. The idea is that you can have either perfectly periodic structures or even some random structures. You can have these localized states that are possible in that. All right. So this was the beginning, and we will spend some time trying to understand how this happens. Okay. So to understand this, let's go back to our familiar dispersion relation we talked about. So this is a dispersion we talked about, right? If you have a light line, let's say omega equal to ck, and if I consider any medium, well, the light line will be shifted to the right. So there is this refractive index that comes into picture. This is probably we talked about in the first week of the course. So now what we'll do is we'll consider an extension. Okay, this is for a homogeneous medium. Now we'll start looking at what happens if you have inhomogeneous medium. What is an inhomogeneous medium now? So that would be something like this. Let's consider maybe a slab like this. Let me say this is a slab of gallium arsenide of epsilon, let's say epsilon 13 in this case. Okay, that's what we are taking in the next slides. So if you have such a slab, just for analysis purposes, right now I'll introduce some periodicity in that. I'll say this slab, so it's going to be cut into multiple pieces and kind of they're arranged together. So I'm forming a lattice out of this slab. Right now it's all same materials, so it should still be similar, but we are introducing this periodicity just to analyze this. Okay. So let's say the periodicity is A. Okay, this is a periodic structure. Okay. Well, if the light is propagating here in this sort of periodic structure, but with the same material, right? So if I call this as epsilon of 13 here, essentially everywhere you have gallium arsenide, epsilon is 13 only. Okay. But I'm just introducing the periodicity to analyze. So what do we think will happen? Okay. It turns out that, when the wave vector reaches certain specific numbers, some interesting features can occur. Okay, that's what we want to introduce now. So let's redraw this dispersion relation in a slightly different form. Well, the same form, but that will help us to take the concept forward. So now I have, let's say, omega versus k. This is a straight line like this. And then correspondingly, there's another straight line. Right? So now what happens is we want to understand what happens at k equal to, let's say, pi by a. Okay, I want to understand what happens. Why am I interested in this? Well, you will see in a moment. Let's say what happens if k equal to pi by a. When k is equal to, we know that k is 2 pi by lambda, and that is equal to pi by a. So what does it mean? Right? If I consider a scenario where the lattice constant is essentially lambda by 2, something interesting happens. That's what I'm claiming. Okay. What does it mean? Lattice constant is lambda by 2. Well, the wave could be something like this. You have the first part of positive half of the oscillation and then negative half. This is a wave which k equal to lambda, a by 2 or 2a, lambda equal to, in this case, lambda equal to 2a or a equal to lambda by 2. This is one particular wave, right? I mean, you can also think of a k which is in the negative direction. It doesn't really matter for us. So even pi by a, it's a negative propagating wave essentially. So even in, let's say if I have minus pi by a, that is going to be same. Okay. Similarly, I can even look at 2 pi by a and minus 2 pi by a. Okay. What happens when my k is 2 pi by a? So k is equal to 2 pi by a. That implies, in this case, a is going to be turning out to be lambda. So essentially my wave vector, the periodicity is equal to wavelength. Okay. So such a wave could be something of this form. The whole period is basically confined to one particular unit cell. Okay. I mean, I can even generalize it, and I can tell you that whenever A equal to n lambda by 2, any integer multiple, n equal to 1, 2, and 3, and so on, some interesting things happen. N equal to 1, 2, 3, and so on, some interesting things happen. All right. And what are those interesting things? Well, essentially, we borrow the ideas that were introduced by Bloch in solid state physics, right? So what we are talking about is now electric field. So I can think of my electric field now as a Bloch wave. Okay. So if an electromagnetic wave is propagating in just a medium, we said it's exponential. Okay, since this week I'm considering minus ikx, I'll take this. That's a plane wave propagating in the positive direction, right? Because we took the exponential I omega t notation, not minus I omega t notation. Okay, so just make note of this. So if you have this notation, exponential minus ikx, the electric field will essentially be of this form, where my u of x is a periodicity. It captures the periodicity of the lattice, right? So this is my periodic function, essentially meaning u of x plus a equal to u of x. If you translate the lattice by, let's say, the periodicity, then you get the same lattice. That's all. So that's a Bloch function. Okay. Now, if you have such a Bloch function, what happens? Well, we can look at what happens to electric field. So let's go back. So now, what is my E of x plus a? That's going to be u of x plus a exponential minus ik x plus a, right? So it turns out to be equal to u of x exponential minus ikx and exponential minus ika. But now, when a is equal to lambda by 2 or n lambda by 2, this entire thing, you can see it quickly, is equal to e power minus I pi, or plus or minus I pi, I should say. I pi. When when periodicity equal to a equal to n lambda by 2. So essentially what you are seeing is the electric field itself is going to be exactly identical. If you go to, let's say, higher case, at this particular case, even if you introduce a shift of, let's say, pi by a, the electric field is going to be the same. Okay. So this is equal to E of x at a equal to n lambda by 2. Or if I want to write in terms of k is equal to n pi by a. At those case, essentially the electric field is periodic. Okay. So what happens is, so what we can conclude from this is that, I mean, the distribution of electric field is the same, so slightly energy is different, that's it. So what we can do is, instead of having a dispersion relation like this, we can truncate it, because this range is what is known in the literature as the first Brillouin zone. First Brillouin zone. So what it means is this first Brillouin zone has all the information that you need. Even if you consider, let's say, a wave, let me draw a segment of the wave here, this particular segment from pi by a to 2 pi by a, let me say, or 3 pi by a, in fact, actually it's going to be. That is not going to have any new information, because if I translate it by pi by a, if I increase by pi by a, I'll see that the energy becomes the same. So basically, I can redraw this dispersion relation in this form, only in the first Brillouin zone. So what I'll draw is this. I can bend my dispersion now. You can have a scenario like this. So instead of dispersion relation extending out into all space, I'm going to have dispersion only in the first Brillouin zone, and that gives me all possible data that I need. Okay. So this contains all the information. about wave propagation. Why is that? Because even if I translate it by that, the energy is not going, the energy is not going to change. So I can just shift that in K. Okay. And that's why I bring it into, fold it back into the first Brillouin zone. So the reason I'm introducing this idea is that from now on, you'll see in the next slide here, you see how the band structures will change when you have periodic structures. Okay. So let's look at this now. So on the left is something that we have already described. So this is basically having, let's say, layers like this, multiple layers like this. Okay. Each of them having the same periodicity, okay, same material. So epsilon equal, it's effectively a homogeneous medium. And basically you have this dispersion relation here is going up to pi by A. You see here, it's K. Okay. We are using a slightly different notation, which is very popular in the photonic crystal community. This is called as a normalized frequency. This is called as normalized frequency. The reason we, this essentially means, here, the idea is that Maxwell's equations are scale invariant. That means that we did this analysis, let's say at optical wavelengths with some size factor A. Now if I change my size factor and make it much smaller, if the dielectric constant, if we account for the right dielectric constant, the same ideas will work even at X-ray wavelengths. So a mirror that I can design at optical frequencies, the same idea can be used to design a mirror at extreme UV or even in X-rays. Okay. Essentially your atoms, a material like silicon works like a X-ray mirror. Okay. Because you can do diffraction and all that, right? So similarly, if you go to longer sizes, if I increase my periodicity, I can have RF waves propagating in such a structure and they can actually have the same behavior as this. So you don't need to specify what frequency. So we talk of it in terms of normalized frequency. In this case, omega is basically 2 pi nu, and 2 pi c will cancel out. So you will essentially get, this is A by lambda. Normalized frequency means we are talking in terms of, it's a dimensionless constant. Okay. This is dimensionless. So the moment you decide the dimension of A, that tells you what frequency we are talking about. Okay. So we can apply the same analysis at optical frequencies, at X-ray frequencies, or at RF frequencies. Okay. Of course, you have to take the right dielectric constant into account. Similarly, the bottom is basically a normalized wave vector. Dimensionless again. Okay. So what does it mean? In this case, K, if I say that K is, K into A by 2 pi, what does it mean? K equal to this much, right? So if I put K equal to, this is Ka by 2 pi equal to 0.5. That implies this will go out and in this case, K will be equal to pi by A. That's it. Okay. So this is my pi by A that I talked about, and this is my minus pi by A. Okay. So these are the extremes. In those extremes, that's why the bands are bending back and you see this. So now something interesting happens when we introduce slightly different materials. So in the second graph in the middle graph here, these are alternating layers with dielectric constants epsilon equal to 13 and epsilon equal to 12. One of the practical realizations of this would be, take gallium arsenide. Gallium arsenide has a band gap of 1.42 eV and let's say roughly it has an epsilon of 13. Now have a structure with gallium aluminum arsenide. Aluminum arsenide has a band gap of I think 2.1 eV or something. So it has a slightly higher band gap. So it will have a slightly lower refractive index. So gallium aluminum arsenide will have a refractive epsilon of roughly 12 in this case. This is the assumption. If you take a structure consisting of this very small change in epsilon, okay. So I build a multi-layer out of it. When I can build it like, I can have this gallium arsenide layer, again another gallium arsenide layer, another gallium arsenide layer and so on. In between I can have a gallium aluminum arsenide like this. So I can actually think of a material which consists of two sublattices. So I can have a gallium arsenide sublattice and a gallium aluminum arsenide sublattice. What do you mean by sublattice? Essentially think of this structure is effectively one structure consisting of this, right, of red, another structure consisting of blue. Okay, essentially they are combined with each other. Okay, when you have such a scenario, it turns out that a small photonic band gap occurs. Why do you know that is what is shown here? So now the dispersion here, which is going here all the way and then turning back, instead there's a small band gap that occurs roughly, at some normalized frequency. Why does that happen? How do we understand this? Well, if these two sublattices were slightly, are far away, at that particular k, right, you will see that there is no, the energies are the same. Okay. So you can understand this from the hybridization perspective that, you can have at the particular k of pi by a, you can have an energy level at, let's say, for the gallium arsenide sublattice. Okay. And then you can also have another energy level for a gallium aluminum arsenide sublattice. Okay. No, they're very far. The energy levels can be identical. But the moment you bring those sublattices close to each other, that means you overlap them to form this crystal. So this was one energy level, this blue was this is one energy level here, one energy level. When both of them are superposed, that means you're bringing them in close contact, the energy levels have to hybridize and you end up getting one level here and one level here. Okay. So this is band gap opening due to mixing of sublattices. Okay. All right. Does it make sense? So that the hybridization concept we talked about all the time, right? Okay. Something more interesting is there in this. That is, how does the wave behave in these two different structures? Effectively, what it means is you can have one solution wherein the wave is confined to the high refractive index. So in this case, the electric field is in epsilon equal to 13 medium. Okay. Whereas in this case, the E field is in epsilon equal to 12 medium. So you have these electric fields which are confined in this structure. So that's why we call this as a dielectric band usually. Dielectric band. And then the air band. Air in the sense just that it's a lower dielectric constant medium. That's all. Okay. That's the notation we typically follow. So, I mean, the top two graphs of the electric field, if you look at the amplitude, the amplitude of it, you'll see that, it's effectively in this high energy is in the high refractive index or low refractive index medium. Okay. That's a physical origin of the band gap. And something interesting also happens. You can also think about it like, a wave which is propagating now in these structures, and there are these reflections that are happening. So when the wave periodicity matches the periodicity of the structure, multiple reflection can occur, and then there's a strong buildup of energy. There's a large density of states that are available. So that's why we already told you about the dispersion relation, and we said the density of the electromagnetic waves in this, density of states for the EM wave is going to be proportional to d omega by dk. Okay. So whenever you hit these points, you'll start seeing that there's a large probability of wave confining, a wave having this particular wave vector and this particular energy. That's why these are called as, in a way, these are similar to the resonances we saw for the SPPs. Okay. So the dispersion becomes flat. When you're far away from this, the dispersion follows the light line. But as you approach the band gap, the density of states increases and the dispersion flattens out. Okay. So this is what we are seeing right now. So, you can even more extend this. Now consider a structure with even higher contrast between dielectric materials. So now the third graph now is with alternating layers of epsilon equal to 13 and 1. Epsilon equal to 1 means air. So air separated by gallium arsenide layers. How will you build it? Okay, right now it's a theoretical thing we are looking at. We don't have to worry about building it. We'll definitely not be able to do air, but we can think of transferring layers and then building a stack of gallium arsenide at 1.5. Epsilon equal to, glass, refractive index equal to 1.5, epsilon equal to 2.25. We can try to definitely build it. Okay, so even in this structure, when the contrast is higher, you see that the band gap is much bigger now. So large band gap opens when you have structures with a higher contrast. All right. So to summarize, what happens when you have periodic structures? Well, when you have periodic structures, electric field is now, there is a range of frequencies which are not allowed. So this is a band gap, right? Photonic band gap. And above and below, just below the band gap, you have a very large density of states for wave here to have a solution here and here. So that those correspond to, this is a dielectric band and this is the air band. So where the energy is confined, you see this. And interestingly, the amount of band gap. Now, we said this is normalized frequency. Okay. So if this is my normalized frequency, what, okay, norm, right? Let's say if my periodicity was A, and now I increase my periodicity to, let's say some alpha times A. What happens to my frequency? Now frequency will reduce by omega by alpha. Okay. So it's not useful to just simply talk of band gap. It's not useful to simply talk about delta omega. Delta omega is the band gap effectively, delta energy. Whenever you say what is the band gap of silicon, we'll say 1.42 eV. The difference between the Fermi in the conduction and valence band. That's all we are saying. Sorry? Oh, sorry, yeah, dielectric band gap of silicon is 1.12 eV. Gallium arsenide is 1.42 eV. So, yeah. So, yeah, it's not enough to talk about delta omega because this is normalized frequency. So what we talk about is what is known as band gap to mid gap ratio. So instead of only this, I'll take the energy in here. Let's, for example, in this case, roughly the band gap delta omega in this picture is what, 0.1? 0.1 divided by 0.2. Is this correct? Yeah. Okay. So roughly delta omega by omega, band gap delta omega, the mid gap is 0.2 normalized frequency. So this is roughly half. Okay. So by choosing the appropriate lattice constants, we can think of a photonic crystal at RF frequencies or at X-ray or optical frequencies. So this band gap to mid gap ratio is going to be dependent on, we saw already, this delta epsilon. So this is the permittivity contrast. If you have larger permittivity contrast, you're going to have much higher band gap. We saw that already. When you had epsilon equal to 12 and 13, it was very small band gap. But the moment epsilon is 13 and 1, it's a large band gap. And of course, there are other things. This is essentially a dimensionless quantity. Okay. And this familiar, if you have studied the electronic band structure for chronic penny model in semiconductors, you'll see the similar sign dependence. Essentially saying that close to the band edge, the bands become flat. A large density of states which is possible. All right. So this is the origin of photonic crystals, photonic band gaps. So in the next lecture, we will talk about how, this can be extended to higher dimensions, and also, yeah, we'll look at other features of photonic crystals. All right. Thank you so much for your attention. I'll see you in the next lecture. Bye.